This is AJ from Radius. I'm co-founder of Radius, and thanks for having me here. Today's talk will be about encrypted mempool that we've contributed to Starkware community, and also about share the sequencing layer for rollups. So here you might be not familiar with a sequencer for rollups. Sequencers usually received transitions from users and build a block, and then execute the block, and then post the result and the ZK proof to Ethereum or starknet. So I'm here to help developers who want to build their own rollups or even the layer 3 on starknet. So let me just go through what Radius has been building. Okay, so actually I'm here because I believe in layer 3 app chains. So basically the concept of fractal scaling. So, but deploying rollups is kind of really difficult, not easy, because developers usually use smart contract to develop their app. It's kind of easy, and then there are a lot of reference codes, so it's really easy to develop your own dApps based on smart contract. But even though rollups has really great advantage like scalability or flexibility about your projects, but it's not that easy, because one challenge part would be to run sequencing node by yourselves, because you need to come up with economic incentives to give sequencers, and then running your sequencer thing, it's kind of difficult. So that's when I found that there is a rollup SDK called Madara in Starknet community. So I took a chance to contribute to Madara SDK, so we just help developers to deploy their rollups quite easily. So today talks about the progress that we've been made for Madara. So we've done implementing encrypted mempool. So anyone wants to have your own rollup network MEV or censorship resistant, you can use our encrypted mempool with the Madara project. And then another task that we've been doing is to develop a shared sequence layer for layer 3 developed by with Madara network on starknet. But sequencers right now is really important to decentralize sequencers for rollups. But decentralization is a little bit different from the one that we usually take on layer 1, because usually rollups inherit security from this Ethereum or starknet based layer. So decentralization of sequencers would be more to operate rollup network transparently. So if you care about a censorship or liveness or even governance, you should come up with some way to decentralize sequencers. So there's two ways. One is that to have multiple sequencers doing same thing, and you can have a consensus between them. But we took a modular approach to decentralized sequences, split features are builders to build a block, proposers to execute and post the result to Ethereum or starknet. And then another one is that for ZK rollup to generate the ZK proof, it's a prover. So our sequencing layer helps those three entities to communicate and operate quite fluently. But the problem is that we want to adopt PBS, Proposer Builder Separation Scheme to rollups, but there are some problems, because rollups is actually a scaling solution. So, which means that pre-confirmation on user side is really important. So if we adapt this PBS scheme to rollup sequencing side, there should be additional latency for pre-confirmation thing. Like after proposal builder block, and the user can get pre-confirmation from these sequences. So it's a kind of a not wanted situation. So our solution is to use encrypted mempool and all the commitment things. So we can make this pre-confirmation faster, and then we can provide a good user experience when they use rollups. So basically, it goes like this. And the user encrypts their transactions, and the builders, when builder receive these encrypted transactions, they respond to user with a pre-confirmation that saying that your encrypted mempool, your encrypted transactions is going to be included in a specific order of next block. That's a pre-confirmation thing. So how it's possible? Its transactions is encrypted because builders or sequencers cannot see the contents of the transactions. So builders cannot manipulate the order of transactions. So so builder responded to users with the order commitments. So and the user make sure that their transactions gonna be included somehow. And then also, as I said before, if using when using encrypted mempool, we can make sure that there's no censorship or MEV resistant. The rollups is going to be censoring and MEV resistant. So, basically, if you are not familiar with the MEV stuff, MEV is all about the ordering. So because currently the transitions are public, builders or sequencers or validators can manipulate the order to extract value from your pocket so they can make some profits from them. So we'd like to prevent this attack by encrypted mempool. So builders cannot see the contents of that. So that's why we can provide this censoring and MEV resistance features for rollups. So I will go deep into how it works. First of all, encryption scheme, we use delay or time lock puzzle encryption, which means that the solution to time lock puzzle would be encryption key. So if sequencer receive encrypted transactions, they need to solve time lock puzzle to find a decryption key. So during this time lock puzzle, a sequencer have to respond to user with the order commitment saying that it's like a pre-confirmation your transactions. So this is how we protect the user from this censorship and MEV attack that can be happening on sequencer side. So this is the whole architecture. So what if a sequencer break this order commitment that he just gave to user side? At that case, and the user can claim to somehow some kind of a smart contract on Ethereum that, okay, this order commitment that I received from sequencer side is kind of broken, it's not kept. Because it can happen because sequencer usually store transaction hash lists on smart contracts on Ethereum. So a user can claim with this order commitment to smart contract on Ethereum. So smart contracts can easily verify this claim. So if these smart contracts find out order commitment is broken, sequencer will be slashed. So that's how we force this order commitment is kept. So this encrypted mempool and order validation thing, we can protect our end user side from this MEV or censoring attack. But how about the sequencer side? There can be a malicious end user who wants to attack sequencers. They can make invalid encrypted transactions, but its transactions is encrypted, so a sequencer cannot distinguish it's encrypted, it's valid or not. So it might, a sequencer might waste their computing resources or block space because it cannot distinguish this encrypted mempool is valid. So it would lead to a network instability. So that's why we applied a ZK proof to prove that this encrypted transitions is valid without decrypting it. So there's two things the end user need to do when creating a transition. So they need to encrypt transitions and also generate a ZK proof to prove that this whole encryption process is done correctly. So this using ZK proof on sequencer side, they can verify this encrypted transitions is valid. So there's no waste on computing resources or block space. So that's how we protect a sequencer from possible attacks from malicious end users. So another one that I'd like to emphasize is that, as I said before, sequencing is, liveness is really important. Because that's why we cannot have centralized sequencers because it's a single point of failure. So, right now, Radius is doing the consensus-based sequencing sets to provide liveness to rollups. So there are a bunch of sequencers who wants to become sequencer for specific rollups. So we are gonna randomly select sequencer sets for each rollups, and then it's gonna be a VRF used for that. So consensus model will be leader-based. So when a user sends encrypted transitions and ZK proof, a leader can respond with all the commitments. So leader take all responsibility to build a block and everything goes correctly. Another one is that another advantage that this sequencer layer can provide is that I think the interoperability between multiple rollups. Rollup approach always be criticized because fragmentation can happen. But I think the shared sequencer layer is well positioned to solve this fragmentation thing between multiple rollups because shared sequencing layer has a full control of building blocks. So whenever there are some kind of let's say flash loan transitions or cross rollup transitions, sequencer can make sure that every transitions related to this cross rollup transitions is going to be included in next block for multiple rollups. So that's how we can guarantee atomic inclusion thing. But the problem is that atomic inclusion is not enough to guarantee this interoperability happens. We need somehow called atomic execution because sequencer can include those transitions in a block and then deliver that block to rollup side, but it cannot guarantee that this block actually executed. So that's why we are researching on this atomic execution thing. So basically, auto validation can be used to make sure that this atomic execution happening between multiple rollups. So, and then sequencer stores all states of rollups interacting with the sequencer layer, and then also tracking all cross rollup transitions, so we can make sure that if something goes wrong with this cross rollup transitions, it can roll back to the place that multiple rollups should be. So that's but it's kind of really difficult to figure out. So it's a kind of a researching stage to implement this. So okay, so if you want to use our encrypted mempool with Mandara, you can do that. You can deploy rollup the Mandara with encrypted mempool if you use our GitHub repo, and then we just wanna support these millions of rollups because we believe that there will be a tsunami of ZK rollup is going to be happening because there's a lot of advantage that you can get if you choose to build rollups, not like based on smart contracts. Okay, that's the end of my talk. Thank you.